Chapter 4 is about the operational amplifier, so-called we call op-amp. It looks like this, and we're gonna have resistors. They're connected to the positive terminal or negative terminal and so on. It's a short chapter. So op-amp is the single most important integrated circuit. It is a versatile interconnection, transistors and resistors. I'll show you inside of this op-amp and expands our capabilities in the circuit design. And we use this op-amp a lot. The op-amp is the electronic unit. It's kind of like voltage control the voltage source. And it is an active circuit element. And we can use this op-amp. We can do addition, subtraction, multiplication, and division, even differentiation and integration of the values in the circuit. And this op-amp models, it looks like this. There's a 14 pins inside of this chip. There are 4 op-amps. Obviously, there are 2 inputs and 1 output, 2 inputs and 1 output. This is the schematic for the power and the ground. And inside of the op-amp, we have this. So there's a positive terminal, negative terminal. This side is a triangular shape here. And this is the output. And there's the gain, A naught times V in, and then all of I. We don't have to worry too much about inside of the op-amp. So here's the op-amp diagram. And we're going to make this op-amp as ideal op-amp, not real applicable. As the difference between the ideal versus actual op-amp is really small. When we analyze the circuit, we said this is the ideal op-amp, and if this is the ideal op-amp, there is no current going into the negative terminal, there is no current going into the positive terminal, and outside the voltage, V minus and V plus, they are going to be equal. We have V minus V plus is equal, A minus A plus, they are all 0. It looks a lot, but it's not. And then we're going to use nodal analysis for those nodes and then solve the problem. Let's work on this. We ready? We need to find gain. So in the op-amp, the gain defined by output over input. Voltage output over voltage input. So in this case, gain is V out over Vs. The first thing, we want to identify negative terminal or positive terminal going in, and we're going to name them V minus, V plus. That's what we said in the book. I'm going to just call it V1 and V2. So first step, we're going to let V1 equals to V2, always. So you identified the node in front of negative terminal, in front of positive terminal. These are the 2 nodes, and we're going to let them equal to each other. And then second, you say I minus equals to I plus equals to 0. This is I minus, this is I plus. They are equals to 0. There is no current going into that negative terminal. There is no current going into the positive terminal. That means wherever the current going into V1 node, this I1 should be the same as this I1. The current go through R1 is the same as current go through R2. Make sense? Because there's no current going in. In real op-amp, there's very small current going in. There's some current going out from here as well. Same thing. There is no current going that direction. That means there is no current going in that direction, right? And this is the negative terminal. Therefore, there is no current. And in this case, in this problem, V1 equals to V2. That's always true. And also that equals to 0 because V2, there's no resistors or nothing connected to V2. Therefore, V2 equals to 0. After this, we need to do the nodal analysis for this side. What is the value in this node? It's a Vs, right? So the nodal analysis is voltage Vs minus V1 over R1 equals, that's the entering, and now leaving is V1 minus V out over R2. Because this guy is V out. From here, we said V1 equals to 0, then Vs over R1 equals negative V out over R2. So we want to multiply both sides by R2. Then we have negative V naught equals R2 over R1 times Vs. Now we're going to divide both sides by Vs, negative Vs. Then negative R2 over R1 equals V naught over Vs. R2 as a 1000 ohm, R1 as 100 ohm. Then if you supply 10, output is going to be 100, 10 times more. So we get the gain of 10 if you properly choose R2 and R1. Okay, we ready? So this is one node. I'm going to call it V1. And here's the another node, V2. Then we have V1 equals to V2 equals this time what? That's the 12 volts. Yeah, so in this diagram, I mean, it's the same thing. So again, just like what we saw in the chapter 3, the bottom line is going to be 0. V1 equals to V2. That means this guy is also V2. Now for the node analysis, we're going to say current going down, current going down. This I is the same as this I because there is no current in and out for this negative terminal. So let's do KCL, the nodal analysis at V2. Entering equals V0 minus V2 over 12K equals leaving V2 minus 0 over 2K. I just did the KCL at V2 right there. And V2 we set 12. So that is V0 minus 12 over 12K equals 12 over 2K. We're going to multiply 12K for both sides. Then V0 minus 12 equals 12 times 6, 72. Then V out equals 72 plus 12, which is 84 volts. Now how we find I sub naught? Any suggestions? So voltage across here is same as the voltage across here. How? They are parallel. Good, good. Now what is voltage across here? 84, right? That's what we calculate. V naught is there. So that's it. So I sub 0 equals V sub 0 over 10K. That is 8.4 milliamp. Okay, let's do this. V in equals to 2 volts. And then find I naught. Okay, I'm gonna call this as a V1. This is V2. That means this is V2. Current going downward. Current going downward. KCL at V2 in the here. Entering, this is V out. So V out minus V2 over 20K equals V2 over 3.3K. This circuit V1 equals to V2 equals to what? 2. Therefore, V0 minus 2 over 20K equals 2 over 3.3K. And you use your calculator, find V0 as 14.12. And this I naught is going around here. So again, I naught equals to V out over 23.3K. That is 0.606 milliamp. So let's do this. Okay, we need to find R1. So what is R1? And another information is given. Gain equals to 10. That means V out over V1 equals to 10. So what we need to do, so this is V1 and this guy is gonna be V2 and V1 equals to V2. I'm gonna just call this V1. Since V1 equals to V2, we can call this as a V1 as well. And we have a current going in that direction and the downward, or going up and to the right, it doesn't matter. Then this current first. So we're gonna do KCL at V1 entering that is V out minus V1 over 18K. That should be equal to V1 over R1. Now I'm gonna just separate this guy, and we have a V out over 18K, and at the same time we're gonna move this to the left side. So minus V1 over 18K minus V1 over R1 equals 0. Sorry, let's move this guy to the other side. It's easier. We have 1 over 18K plus 1 over R1 times V1. Now we're going to multiply 18K for both sides. Then we have a V naught equals 18K over 18K plus 18K over R1 times V1. And then we're going to divide both sides by V1. And we have a V out over V1 equals 1 plus 18K over R1. What is gain? V out over V1 is given as a 10. From here, 1 plus 9 equals to 10, right? Therefore, 9 equals 18K over R1. 1 over 9 equals R1 over 18K. Therefore, R1 equals 18K over 9. Therefore, R1 equals 2K.